We introduced Generative Scene Networks, a generative model which learns to synthesize radiance fields of indoor scenes. This is a joint work by Terence DeVries, Miguel Angel Batista, Natasha Srivastava, Graham Taylor, and Joshua Susskind, representing a collaborative effort between Apple, the University of Guelph, and the Vector Institute. Our goal in this work is to learn a distribution over complex, realistic indoor scenes. Learning such a scene prior could be useful for a variety of difficult downstream tasks, such as content creation for augmented and virtual reality, scene completion, scene editing, mapping and navigation, or as a world model for reinforcement learning. Our generative scene network architecture follows an adversarial learning framework, where the generator tries to map noise to realistic-looking images, and the discriminator tries to distinguish between real and fake images. Here we show the architecture for a standard 2D image generating GAN with a convolutional generator and discriminator. To generate 3D scenes instead of 2D images, we can replace the convolutional generator with a conditional MLP that parameterizes a radiance field. The MLP maps 3D coordinates and latent codes to color and occupancy values, allowing us to render images by sampling points along camera rays and combining them via volumetric rendering. During training, we sample radiance fields and render images from them at random camera poses, which are then passed to the discriminator as in a standard 2D GAN. This architecture works well for generating single images, but for complex scenes, we found performance to be limited. In particular, each scene is represented by a single large radiance field, which may be difficult for the MLP to encode with high fidelity. To improve the expressiveness of the generator, we map the global latent code Z to a 2D grid of local latent codes W using a convolutional decoder. These local latent codes can be interpreted as a latent floor plan representing the scene. Conceptually, this strategy decomposes the large scene-level radiance field into many smaller, local radiance fields, which are more manageable for the MLP to represent. Additionally, we replace the global coordinate system with a local coordinate system aligned with the local latent grid. This substitution makes the local latent codes spatially independent, such that they can represent the same radiance field irrespective of their global position. Once trained, we can sample scenes from the learned prior and render them from any arbitrary camera pose, allowing for unconstrained sea exploration. Here we demonstrate some scenes sampled from our model after training on the replica dataset. In addition, we can also use the prior learned by GSN to invert observations and fill in missing parts of the scene. Given a trajectory of images through a real scene, shown on the left, we invert GSN's generator to find a scene radiance field that minimizes our reconstruction error. We can then render from this radiance field to complete the rest of the trajectory, as shown on the right. Finally, we demonstrate how the latent floorplan W can be used for spatial scene editing. In this example, we mirror the local latent grid, resulting in a mirrored version of the scene when rendered. In conclusion, we introduced Generative Scene Networks, a generative model which learns to synthesize radiance fields of indoor scenes. We showed that decomposing large radiance fields into a collection of many small, locally conditioned radiance fields improves generation quality. Finally, we demonstrate that GSN learns a useful scene prior, which can be leveraged for several useful downstream tasks.